We are now finally ready to talk about Greens Theorem, and that's what we're going to cover in section 6.4. So right now I have on the screen Greens Theorem, what we're going to call the circulation form. We'll learn also the flux form of Greens Theorem as well. So this theorem is saying if you have a simply connected region, and that's what I have shown in blue. Let me get my pointer, there we go. Right here, this is a simply connected region. It doesn't have any holes in it with a piecewise smooth boundary. Okay, so has a smooth boundary oriented counterclockwise, so pathway is counterclockwise. If M and N, and remember those were the letters we were using for the components of our vector field. So if those components have continuous first partial derivatives, then, all right, so this is saying if we integrate our vector field along this path C, so we're talking about a line integral. If we want to find the line integral along this path C of this vector field, and this notation right here, the second thing, these mean the same thing, just two different ways of expressing line integrals. That is the same thing as integrating over this area. So we can set this up as a double integral instead and integrate this entire area. And the quantity that we're going to integrate is dn dx minus dm dy. So that's what Greens theorem is saying. It's saying that we can convert a line integral on a closed line, closed path, I guess, into an area integral. And there are cases where one is going to be easier than the other. All right, so let's see how that works. The following problem says use Greens theorem to evaluate the following. And this line integral is written in that differential form. So basically this is saying, okay, let's integrate along this path. Notice it's going counterclockwise. And our vector field has an x component of 2x squared plus 3y and a y component of minus 3x squared. So we're integrating that vector field along that path. Greens theorem says we can convert this into a double integral over the area of that region, which in this case I do actually think is going to be easier. The line integral, we would have to find the three separate paths and compute three separate integrals. I think we can get this one set up as one integral over the area of that region. Okay, so my m is 2x squared plus 3y. My n is negative 3y squared. My, so derivative of m with respect to y is 3. Derivative of n with respect to x is 0. And so one thing to notice here, my my does not equal my nx, and so this is not a conservative vector field. So we wouldn't actually be able to use that fundamental theorem we learned in the last section. So what Greens theorem says is we can take nx minus my, so 0 minus 3, and we can actually integrate negative 3 over the area of this region. And so I'm going to set this one up as an integral. It's good to review how to set up these double integrals for area. Although in this particular case, we are actually talking about a triangle. And so we could actually just find area of that triangle and multiply it by negative 3, and that would be our answer. But let's actually make sure that we remember how to set up double integrals over regions in the plane. So basically, I have right here is the line y equals x, goes through the origin and the point 1, 1. And then on the other side, I have the line y equals 2 minus x, and then the bottom boundary is y equals 0. So if I want to set this up as one integral rather than two, I'm going to do the x's first. And so the x's start on that line y equal x, and they stop on the line y equals 2 minus x. So my bounds of integration for the x's go from y to 2 minus y. I guess I kind of didn't show a step there. Because I was integrating the x's first, I had to take these equations and solve them for x. So minus x equals y minus 2. So x equals negative y plus 2. That's how I got that 2 minus y right there. Okay, and then the y values are going to go from y equals 0 to up here, y equals 1. So there's the integral I'm going to find. We'll do that inside integral first. So we're going to integrate negative 3 with respect to x. We get negative 3x. Plug in my bounds of integration and subtract. I did some distributing, combining like terms, and I got negative 6 plus 6y. Then I'm going to do my outside integral. So I'm going to integrate from 0 to 1, that answer, negative 6 plus 6y. I'll integrate that with respect to y. Let's see, negative 6y plus 3y squared. Plug in the 1, plug in the 0, and subtract them, and there's my final answer of negative 3. So I guess the other thing I do want to note here, again, I set this up as an integral because I wanted us to practice that concept. But notice that we do actually have a triangle. The triangle has, let's see, if this is the point 1, 1, our triangle has a base of 2, a height of 1. So the area of that triangle is 1. So negative 3 times 1 should have been our answer. And that is exactly what we got when we solved this problem. Now, I do want to show you that without Greens theorem, we could have solved this problem, but it would have taken a lot longer because we would have had to set up 3 different line integrals along each path. For the sake of time, I'm not going to talk through all of this, but I did want to just at least have it on the slide. How would we do this without Greens integral or Greens theorem as a line integral? We'd have to come up with parametric equations for all 3 of these pathways. And then we'd have to take our vector field, and we'd have to write our vector field in terms of t for each path. So we'd plug in our x and y into our vector field. We'd find the r prime, f dot r prime. We'd integrate that over our parameter from 0 to 2. And we'd have to do that for each one of these paths. And it barely even fits on my slide. We'd have to come up with our integrals for each one of these paths. Again, I'm not going to talk through this because we did this process in a previous video, but let me know if you do want to see me talk through this. I can definitely do that in class. But basically, all of this in purple was for that second pathway. So again, we take our parameters, we plug them into our vector field, we find r prime, we take f dot r prime, integrate that, and we have to do that for all 3 of these. And then in the end, we end up having 3 different numbers. I got like 16/3 here, negative 43/6, negative 7/6. And if we add all those numbers together, we do end up getting the exact same answer. Here we go. I didn't write it down, but we should end up getting negative 3, the exact same answer. So again, I wanted to put this on the screen just to really illustrate why do we care about Greens theorem. Well, in this particular case, it was significantly faster to recognize that we can treat this particular integral, this line integral, as an area integral. All right, so let's do another one. Let's see if we can integrate f dot dr. So we're integrating a vector or along a path over a vector field. Our vector field is 4y minus 3x right here. And our path is a counterclockwise path around the circle. X squared plus y squared equals 4. So this is the problem we're doing. Trying to integrate along this closed counterclockwise path over our vector field. And so we can set this up as a line integral, or we can set this up as an area integral. And to set it up as an area integral, the thing that we're going to integrate is this nx minus my. And I would like to mention that that quantity, that nx minus my, is actually a measure of the curl or the spin of that vector field. We're going to talk more about that concept in our next section. It just feels weird to not give it a meaning. But again, we're going to integrate our nx minus my over this area, and that'll be the exact same thing as integrating over this path across our vector field. All right, so my m is 4y, so my is 4, nx is -3. Notice they're not the same. This is not a conservative vector field. So I'm going to take nx minus my, I got -7, and I'm going to integrate that over the area of that circle. Because we're dealing with a circle, converting this to polar coordinates makes the most sense. So I'm going to change my dA into an r, dr, d theta. And then my radiuses go from 0 to 2. And then the thetas, we're going all the way around the circle, so from 0 to 2 pi. So if I integrate with respect to r first, I get -7 r squared over 2, plug in the bounds of integration and subtract, that's -14. And then integrate -14 with respect to theta, plug in the bounds of integration and subtract, and I got a final answer of -28 pi. So that is my final answer here for this particular integral. The other thing I want to point out while we're doing this problem is Greens theorem told us what to do when we have a counterclockwise path, which is what we've had in both of our examples. You can still do these problems if the path is clockwise. So if you're moving around that path in a clockwise motion, the only thing that happens is it actually just changes the sign of the answer. And that's just because if you take a line integral in one direction and you compare it to the opposite direction, you'll always get the same answer but with opposite signs. And so that's true here as well. And so if this problem were a clockwise path, I could actually do it the exact same way, but then I would just change the sign of the answer, and the answer would be +28 pi. All right, here's another one. Let's see if we can find the integral y dx plus 2x squared dy for the path that's shown in the picture. So this is an integral written in that differential form, but it really isn't any different. We've got our m is y, our n is 2x squared. Derivative of m with respect to y is 1. My derivative of n with respect to x is 4x. So I'm going to integrate 4x minus 1 over the area of this region. Once again, we have some circular shapes, so I think doing this in polar coordinates makes the most sense. So the dA becomes the r, dr, d theta. I'm going to replace the x with r cosine theta. So I have to integrate 4r cosine theta minus 1, and then times r, dr, d theta. In this problem, the r values are actually starting at 1 and stopping at 2. So 1 to 2. And then we're only on the top half of a circle, so my angles, my thetas, start at 0 and stop at pi. To integrate this, I'm going to distribute the r. So I'm going to integrate 4r squared cosine theta minus r with respect to r first. Found my antiderivative. 4r to the third over 3 cosine theta minus r squared over 2. I'm going to plug in my bounds of integration. Hopefully I didn't make any arithmetic mistakes. So I plugged in the 2, and then I plugged in the 1, subtracted them, combined like terms. I got 28/3 cosine theta minus 3/2. And then I'm going to take that answer and integrate that with respect to theta. So there's my antiderivative, 28/3 sine theta minus 3/2 theta. I'm going to plug in my bounds of integration and subtract. So I plug in pi. Oh, I just get negative 3/2 pi. Plug in 0, I get 0. And there's my final answer, negative 3/2 pi. So using Greens theorem, writing this as a double integral over a region in the plane, I think was a lot easier than setting it up as a line integral. If we wanted to set this up as a line integral, we'd have to do 1, 2, 3, 4 different paths. Now, when I introduced Greens theorem, I assumed that we had what we call a simply connected region, so a region that doesn't have a hole in it. It turns out we can actually do a little trick, a little tweak, and actually apply Greens theorem to an object like I have shown on the screen. So we want to find the following integral, 4y dx plus 5x dy, for the path shown. And our path consists of moving around I guess it's a square on the outside and a circle on the inside. So my little trick is I can add some extra paths so that this becomes really just one pathway. So what I've drawn, let me try to trace it with my pen. So we can think of this as traveling along the square and then cutting into the circle, looping around the bottom of the circle, cutting back to our square, and then coming back to my circle, back to my square, and then finishing where I started. So basically, I added just a pathway that connects my square to my circle, going in each direction. And so now I can actually trace this object without lifting my pencil. I can trace it exactly once. Now, if we think of this as a line integral problem, when we compute our line integral around what I'm going to call C1, this little line segment, and C2, the line segment that goes in the opposite direction, line integrals along those paths, C1 and C2, will actually cancel out. Because they're in opposite directions, you're going to end up getting the same number with opposite signs. So if we think of this as a line integral problem and we compute our integral along each pathway, these little lines that I have drawn aren't going to actually impact the answer. Because you compute those integrals, they're going to cancel out because you're moving in opposite directions. So adding these little paths doesn't actually change the answer, doesn't change the problem. And now all of a sudden I have a region that I can consider and use Greens theorem on. So I can actually integrate my nx minus my over the area that I have shaded in blue. And so I don't know why I did this. I wrote this wrong. So my my is 4, my nx is 5. Oh, and I did write the integral right because then we would take 5 minus 4 is 1. So we're going to integrate 1 dA over the region shown. So basically, the answer to this problem is going to be the area of that region that I have shown in blue. And so in this case, I am going to take advantage of geometry because I just have a square and a circle. The area of that square that I have drawn is 4 times 4, or 16. The circle has a radius of 1, so it has an area of pi times 1 squared. So this integral should be 16 minus pi. And so I was actually able to do this problem using geometry. We could have set up some area integrals as well, but in this case, geometry was definitely the easiest way to do this problem. So in all of these particular problems, I've been showing you how to compute what we call the circulation form of Greens theorem. And so circulation measures the tendency of a field to move in the same direction as a given closed curve. So it's measuring how much of the vector field is really moving along that path. Whereas the flux measures the rate that a field crosses a given curve. So how much of that vector field is actually crossing our path is flux, versus moving along the path would be circulation. And so all of the integrals that we have found so far were technically circulation integrals. So this f dot t ds, we had learned earlier, this is what our f dot dr integral is. We can integrate our vector field dotted with our normal vector along a path, and that is going to give us our flux integral. And there is a version of Greens theorem for flux integrals. So if you're actually trying to find a flux, if you're trying to integrate f dot n ds, the version of that for Greens theorem says that you can actually integrate mx plus ny over an area region. So it's the same kind of conceptual concept. We have a simple closed curve oriented clockwise. The only difference here is when you're trying to compute like a flux, the quantity that you're integrating, this mx plus ny, is different than when you're doing a circulation integral. So all of the examples I've done so far, when we're finding f dot dr, or we were writing that as m dx plus n dy, these are all circulation integrals. So the examples I did were circulation integrals, but I do want to point out that we can actually use Greens theorem to compute flux integrals as well. That you're going to see an f dot n ds, or perhaps you'll just see the word flux if you want to compute a flux integral. All right, so let's do a flux integral. Let's see if we can compute the flux of the vector field x to the third, y to the third across a unit circle oriented counterclockwise. So for computing flux, we're finding f dot n ds. So that's the integral we're trying to find. Greens theorem says we can rewrite this as an area integral, but the quantity we're going to be integrating is mx plus ny. And well, in the next section, we're going to give some words and meanings to these kind of quantities that we're integrating. But for now, we just have our formula. So m is x to the third, n is y to the third, mx is 3x squared, and y is 3y squared. So we're going to integrate 3x squared plus 3y squared over the area of my unit circle, so radius of 1. Once again, I'm going to put this in polar coordinates. I'm going to replace the dA with this r dr d theta. And then 3x squared plus 3y squared is the same thing as 3r squared. So I'll replace my function with 3r squared. And I'm over a unit circle, so the r's go from 0 to 1. All the way around the circle, the thetas go from 0 to 2 pi. All right, so we're going to integrate 3r to the third with respect to r. I get 3r to the fourth over 4. Plug in my bounds of integration, 3/4. Take 3/4, integrate that with respect to theta, plug in my bounds of integration, and I get 6 pi over 4 or 3 pi over 2, and that is my final answer. That is the flux across that unit circle. All right, that was my last example. As always, please let me know if anything was unclear in this video.